Lewis structure is a nutshell. So what is a Lewis structure? It's basically a representation of the valence electrons for nonmetals. It shows you how they're arranging themselves around an element, whether it's a single element showing how many valence electrons it has, or showing you a compound, which is the more common structure, and how many valence electrons that are shared between atoms involved. It's basically a methodology to show you how the electrons are shared to create the bond. So we have here is CH4, and what you notice about CH4 is that you have one pair of electrons, two pairs of electrons, three pairs, four pairs. These are called bonded pairs. Anytime electrons are shared between an element and an outside element, the center and the outside, or between two elements, period, you have what's called a bonded pair. Lone pair would be something like this. If I draw an H3, and there's two ways of representing electrons, by the way, a pair of electrons. You could draw two dots, or you could draw a line. Each line represents two electrons. I prefer the lines, and that's the way I'm going to show you how to do it. So this is what ammonia looks like. Now, there's 1, 2, 3 bonded pairs here, but there's also a lone pair. This is what a lone pair is. The way you could distinguish a lone pair from a bonded pair, it's not connected to another element. Whenever a pair of electrons are not between two elements, you call it a lone pair. Here's some common Lewis structures for single elements. You can see lithium is group 1A, has 1, beryllium has 2, going all the way to neon with 8 valence electrons. What you'll notice is that the system, this A system, all the way to 8A, tells you how many valence electrons you have for that element. For example, group 5A, which is nitrogen, has 5 valence electrons. So does phosphorus underneath it. Phosphorus also would have 5 electrons. Oxygen and sulfur, which are both groups of 6A, members of group 6A, they also have 6 valence electrons. So the group number tells you how many valence electrons you're dealing with. You're not dealing with metals, so we're going to not really pay attention to lithium and beryllium too much. We'll be moving from the right side of the staircase primarily. Only exception from the left side would be hydrogen, since it is technically a nonmetal. All right, so let's see how to do these. So drawing Lewis structures, first thing you want to do is add the valence electrons for all elements in a compound. So let's start with CCl4 as our example piece. So what I'm going to do is count all the valence electrons available in this compound. So how do I do that? Carbon's group 4A, so it's got 4 valence electrons. Chlorine's group 7A, so that means it has 7 valence electrons. There are 4 chlorines, each of them giving 7. So total coming from chlorine is 28. So what our total is just adding those two together. So you have 32 valence electrons. Place the lowest quantity element in the middle and connect to the rest of the elements in the compound. So what's the lowest quantity element in the situation? It'll be C. And what I'm going to do is connect it to the outside elements. And the way I'm going to connect it is with a single line, which represents 2 electrons. So there's 1 chlorine here, 1 chlorine here, 1 chlorine here, 1 chlorine here. You'll notice I use 2, 4, 6, 8 electrons to do this. So I start with 32, but I've used 8. So now I have 24 valence electrons left. Use valence electrons left to give elements on the outside 8 and put any leftovers on the middle atom. So remember, I have 24 electrons, so watch. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's all 32 electrons were in. I used 8 for the bonding. I use another 24 for the outside chlorines. So that's a total of 32 electrons. So I put all my electrons down. I didn't have any extras in the situation. So as a result of that, we have to look at it carefully and ask ourselves, does everything have 8 that wants 8? And you'll notice that, and the only thing that doesn't want to have 8, FY, would be your hydrogen, which only wants a connection. So 2 is enough. Once you connect hydrogen, you're done with it. And boron, which wants to have 6 instead of 8. Everything else wants to have 8. That covers a lot. If you have extras, if you're short, then what you do, you create a double or triple bond. So after putting all your electrons down, you're like, wait a second, I don't have 8 on around everything. What do I do? At that point, you create double and triple bonds. So I'm going to show you an example of that. So let's do SO3. So 6 for sulfur. 6 for oxygen. There's 3 of them, so that's 6 times 3, 18. So that's 24 electrons. So I'll put S in the middle. There's my connection. Step 1 and 2 are done. I use 6, so how many do I have left? I have 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So there's my 18 electrons, plus the 6 gives me 24. So that's all my electrons. I don't have any more electrons. So at this point, I've done step 1, 2, 3, and I'm at 4. And this one requires 4. CCl4 didn't require step 4 because it didn't have that situation. This one does. So what do I do at this point? Well, I don't have 8. So what I'm going to do is erase and move. Now, why did I erase and move? Because you can share up to 3 lines or 6 electrons between 2 elements. And in this situation, sulfur didn't have 8. It only had 2, 4, 6. So I need 2 more. So how am I going to do that? Just move from the outside elements and share between the 2 of them. Don't take it from here and share it over there. Don't do anything silly like that. When you're sharing, it has to be between the 2 elements that you took the electron away from. So remember that. When you're doing the sharing thing, make sure you put it between the element you took it away from and the middle. And now if you look at it, you have 4, 6, 8. Sulfur has 8 electrons. So you're technically done. All right, some exceptions. Boron, like I said, only wants 6. Elements in period 3 through 7 can actually have more than 8. We'll see some examples of that. Hydrogen only wants 2. So once you connect hydrogen, you're done with hydrogen. So at this point, what we're going to do is try a couple of examples of it. So for chlorine, you have Cl. So first thing we want to do with chlorine is count your total number of electrons. So you have group 7A. So that's 14 total, 7 times 2. So Cl connected to Cl. In this case, either one can be the middle because you only have 2 elements. So we need to put 14 electrons down. We put 2 already. 4, 6, 8, 10, 12, 14. You have to always put all your electrons down before you do anything like double bonding, triple bonding, or anything out of the ordinary like that, because if you try to anticipate too early, you're going to make a silly mistake. So you want to avoid that. So in this situation, chlorine, I put all my 14 electrons. I need to make sure everything has 8. 2, 4, 6, 8, 2, 4, 6, 8. I'm done. That's chlorine. NH3, you have group 5A plus group 1A, and there's 3 of them. So it's a total of 8 valence electrons. So N in the middle, connect, connect, connect. Now remember, hydrogen only wants to have a connection. Once you're done connecting hydrogen, you're done with hydrogen. You don't do lone pairs of a hydrogen. So you use 2, 4, 6. I have 2 left. What do I do with it? Well, remember, according to our steps, if you have extras after you give everything that wants whatever it wants, you stick it off the middle. So that's it. So you have 2, 4, 6, 8 for nitrogen. That's what it wants. Each hydrogen has 2. You're good to go. You're done. CH4, you have 4 plus 4. That's 8. So C in the middle. H, 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 H. And if you notice, I used all my 8 electrons. Everything that wants 8 has 8. Each hydrogen has 2, like it wants to, and the carbon has 8. So you're done. Types of covalent bonds. Single bonds are the ones where you only have 1 pair of electrons. Double bonds when you have 2 pairs of electrons, represented by 2 lines. Single bonds, remember, is a single line. You can see what's going on here. You're sharing 4. And that's because the only way you can give both of them the 8 that they want. Triple bonds, you could share up to 6, and that's the max. You can't go more than 6 electrons between 2 elements. And typically, these are elements that have a total of 10 valent electrons. So whenever you draw a Lewis structure, and you do the first step and you count 10, you're going to have a triple bond. That's almost guaranteed. All right, resonance structure is whenever you have a choice where the double bond goes. The SO3 I drew earlier was a resonance structure because that could have taken and created a double bond on any of those oxygens. Anytime you have a choice where the double bond goes, you have resonance. You see here, I could put the double bond here, or I could put it here. Because I have a choice, we consider this a resonance structure. So resonance is just a fancy way of saying you have a choice where the double bond goes. It's a shortcut that works. Lewis structure for polyatomic ions. Determine the total number of valence electrons. You add the value of negative and subtract the value of the positive charge. So what does that mean in English? PO4, phosphorus has 5, oxygen has 6, there's 4 of them, so that's 24. And what do we do with the negative 3? Because it's negative, we add that to our total. So 32 is our total. On the flip side, ammonium, you have 5 because group 5A, 4 from hydrogen because each of them has 1, and you have a positive charge. So what do you do with a positive charge? You subtract that number of positive charge. So in this situation, I subtract 1, and I get 8 valence electrons. So that's how you deal with charges. You also do need to represent these with brackets. So whenever you have a polyatomic ion, you need to put brackets around the whole polyatomic ion and put the charge on the outside. That makes it clear to the person looking at it that, hey, this is a polyatomic ion, that's why it looks the way it does. So this is the polyatomic ion for CO3 2- carbonate. And you can see I put the brackets in charge. You can see it's also a resonance structure, right? So you can put the double bond on any of these O's. You have a choice. That's very common. All right, so let's try some more practice. CO3 2-. So we have a total of 4 plus 18 plus 2, that's 24. See the middle, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So those are all my 24 electrons, but look at the middle. You always want to look at the middle at the end of everything. Once you put all your electrons down, look at the middle, does it have 8? 2, 4, 6. No, it doesn't. So what do I do every single time it doesn't have 8? Erase and move. And because of polyatomic ion, we need to put the brackets in charge. And because I had a choice of where I did this, I could have done it on this O, could have done it on this O, this is a resonance structure. So I could draw all 3 variations. I'll draw one more to show you what it looks like. So you can see, oops, that's too many. So that's carbonate. And there's a third variation you could draw as well where the double bond goes over here. All right, ammonium, you have 5 plus 4 minus 1, it's 8 electrons. And in the middle, H, 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 H. Everything that wants 8 has 8, including the middle. Brackets, charge, we're done. SO2, 6. O is group 6, and there's 2 of them, so that's 12. That's 18. So S, O, O, that's 2, 4, 6, 8, 10, 12, 14, 16, 18. So there's all 18 electrons. Now at this point, you look at it and you realize, oh wait, sulfur doesn't have 8. So what do? Erase and move. And you notice the steps are always the same. You always put all your electrons down. If you have extra, you take it off the middle. We don't anticipate double and triple bonds. You deal with it afterwards. You should always do double and triple bonds by erasing and moving, not by anticipating. This is not a polyatomic ion, so this is the correct structure. It is resonance though, right? Because you could put the bond here or here. NO2-, that's 5 plus 12, negative, so that's 1 more. So N, O, 2, 4, 6, 8, 10, 12, 14, 16. I have 2 left over. What do? Take it off the middle like I usually do. Brackets around the whole thing with a -1 charge. Now, does the middle have 8? 2, 4, 6. No, it doesn't. So I'm going to erase and move. And once again, you have a resonance structure because I got done it off of either O. And the last one, XeF4, there's 8 for xenon plus 7 times 4. It's 36 electrons. So I'm going to stick Xe in the middle. F, connect first, right? So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I put 32 electrons, but I have 36. I have 4 left over. So what am I supposed to do when I have extras? That's right. Stick it off the middle. I'm going to put it as dots to make it easier to see. It doesn't matter where. As long as there's an empty corner, you're fine. You don't have to put anything specific. All right, let's try some more. H3PO4. So for H3PO4, you have 3 plus 5 plus 24. So that's 32. SO3, you have 8. 6 times 3, 8 plus -2. So that's 26. Sorry, there should be 6, not 8. 24, 26 electrons. For this one, phosphorus is 5 times 2, 10, plus 4 times 1, 4. So you have a total of 14 for this one. So when you draw these ones, for this one, you put P in the middle. What you have less of is goes in the middle. It just works out that way. 1, 2, 3, 4. And I have 3 hydrogens, so I'm going to stick it off the H's. It's a little tougher structure. So I have a total of 32 electrons, and I use 2, 4, 6, 8, 10, 12, 14. So I got to put the rest, right? So 16, 18, 20, 22, 24, 26, 28, 30, 32. There's all my electrons. Everything that wants 8 has 8. We're good to go. We're done. Doesn't matter if the H was on here or here. No. As long as you have 3 O's with H's on it, you're fine. Don't get caught up in location. Location is not the big deal. Just making sure you have the right number of H's on the O's is the big deal. All right, first, so 3, 2 minus, that's in the middle. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 left over. What am I supposed to do with the extras? That's right, let's take it off the middle. Now, does everything have 8? 8, 8, 8, 8. It does. Brackets, charge, we're done. P2H4. So P has to be the middles for both of these. Now I can't put 4 H's. Whenever you have multiple, like carbons, phosphorus, oxygens, whatever, if you have 2 of them, you just bond them to themselves first. It's a little shortcut that works. Like if I had 2 carbons, I would connect the carbons together and then work my way from there. The other thing you always note is that if there's whatever number of hydrogens there are, they share them equally. So there's 4 hydrogens, each of them are going to have 2. So 2 and 2. So you don't stick all, there's your other 2. You don't stick all 4 hydrogens off a single P. That's a big no-no. Whenever you have these multiple P's, C's, N's, whatever it is, whenever you have a duplicate of an element and you have to connect them together first, and then you have these other H's, you just distribute the H's evenly so they look like mirror images of each other. Now I have 14 electrons. I use 2, 4, 6, 8, 10, 12, 14. There's the Lewis structure for P2H4. So that's how you draw Lewis structures for these. The key is just being consistent, doing the same thing every time. And if you do that, this will start catching pretty quickly. But you have to make sure you internalize the steps and follow them the same way. Don't anticipate a double bond, react to it. Once you put all your electrons down, you're short, then do your double triple bond. Don't go in there thinking, oh, there's a double bond, I need to do it now. Just wait. That's going to help you avoid a lot of mistakes.